amazingly good tech failures. So sorry about that. Anyway, welcome to Two Balls. This is the second Rust meetup we've hosted, and we do hope to host many more in the future. So we will start off. We will acknowledge the traditional owners of country throughout Australia and their continuing connection to land and community. We pay our respects to them and their cultures and to elders both past and present. Now, for those of you who don't know much about us, I'd give a little spiel about what we do here. It's a longish talk, so I'll actually kind of race through it a bit. Two Balls is a digital product consultancy. We've got over 100 employees, actually kind of international now, with everyone working from home, doesn't matter. We have a bunch of in-house specializations in mobile development, front-end, back-end, embedded, as well as design and delivery. We also have another little brand called, a brand called Two Moos that specializes in media and game development for kids. We've worked with a whole range of clients, both large and small. We've won a bunch of awards. So with the spiel over, welcome to my talk, which the ironically uncertain title, as the crux of this talk is basically about giving the compiler as much certainty as it possibly can have in order to use all its tricks and heuristics to do all kinds of magic for us. This talk is basically from the perspective of a bunch of grumpy old disgruntled ex-C++ devs. We pretty much, like the embedded chapter here, uses Rust pretty exclusively these days. And the talk the example I'm going to use from is one of those award-winning products we released. And it's basically, a fairly large cross-platform product. And we're trying to use, this is basically our first attempt at using Rust in production for a seriously large project. And we were basically trying to leverage all the benefits that we could from Rust's type system. So this product, and the basis of this talk, is a project that the embedded chapter has been a part of now for quite a few years. It kind of keeps coming back. We basically built what we called the Kaiju Engine, and this is the engine that powers a bunch of apps for kids for a bunch of kids educational company called Wayo. The production timelines for these projects were very tight. They've released a bunch of apps, so one for Wiggles, Sesame Street, Oddbods, and this is on mobile, both iOS and Android. So as I said, the production timelines are very tight, with both Sesame and Oddbods overlapping. These apps have been particularly successful, and this is basically a result of the hard work put in by almost every discipline at Two Balls, from the beautiful apps written by our mobile team and designed by our design team, the CMS content tools produced by the front-end and back-end teams, the art direction and content that came from the art department, delivery that held it all together, and QA that basically made sure it all worked. This was a really huge effort, so kudos to everyone, including Nick. So now that I've hyped it all up, what do these apps do? So the experience grew out of a pretty simple concept. Firstly, the child presented with a video of their favorite Wiggles song, and a bunch of QA people would, grew particularly fond of Hot Potato. And then there's basically a whole bunch of scripted movements during the song. So there'll be a whole bunch of interstitial cuts where the camera, basically it switches to a camera feed of the child, dancing around, singing, having a merry time, and also enjoying this AR experience of their favorite song relevant mask on their face. Particle effects. Basically, this just continues and cuts between kid and song until the experience ends. While the child was grooving away with extra levels of jubilation and all their new AR potato head stuff, the camera clips of their face and the AR mask was all being recorded and serialized so that they could come back and view it later. And if they really liked it, they could then export that to an MP4 so that, it could come back to haunt them on their 21st or something. So that's the high level view of what's going on. There's a whole bunch of other stuff like mini games and other experiences like that. But now with myself being the engine lead and with this being a Rust talk, it's probably time to get into the weeds a bit and have a look at some of the ideas and thinking that went into how we built and designed the Kaiju engine. So with a whole bunch of video clips, audio clips, 3D meshes, particles, effects, transitions, game loops, AR, user-generated content, all being meshed together. We needed some overarching mechanism to bind it all together. So we created this sort of a document format that we called an EDL. This is an acronym borrowed from the film industry, which stands for Edit Decision List. So the EDL basically contains a bunch of events that are grouped together in blocks of time. An event in this case is basically all the different things that the engine can do while presenting an experience. So an event might be something like play a video clip on layer 1 for 100 frames, do an AR game loop, or even just broadcast like a simple message to the host app. So an event here is basically just a declarative entity, as I said, organized in time with some relevant parameters. There are many ways to look at this. And the original prototype engine that we built in Swift, we kind of went with a sort of one-to-one approach where you have a video clip, then you have a video clip class. And this basically proved to be pretty terrible from a code reuse perspective. We had to do a bunch of, later on, as things got more complicated, we did a bunch of refactoring and trying to get things to work, but there's all these odd orderings. And you had to get really kind of super granular in order to make it all slot together neatly. So for the Kaiju engine, we wanted something that was more formal and more granular for assembling these little pockets of code to build functionality out of. Now, I'm a VFX veteran. I come from, building pipeline stuff for VFX, hair, and all this stuff. And so my brain almost always goes to things like DAG structures, graph structures. And so we did end up using a directed acyclic graph or a DAG from here on out to perform all the computations required by an event. So let's take a look at how we might represent, like a DAG, sort of this event thing. So what I'm going to do is I'm going to go through a bunch of slides and just sort of show you some of the original design ideas that we're having when we're sort of building DAGs out of the original Swift engine. So now when we're working through this and the structure, we could see that with the decomposition and the components that might be needed. When I was looking at this, I started to become quite interested in, can we use static dispatch for this? It doesn't necessarily seem so, but can we do it? Now, there is one principle that I always keep coming back to when I'm sort of thinking about software, and that is, if a decision can be made at compile time, it probably should be. And when I was working through all these designs, the structures of the graph looked very static. It's just data that's going into them, right? So is this simply the case? So there's a few more. So now also from these sketches, it becomes apparent that the engine itself requires a whole bunch of resources, and these are often platform dependent. So things like the renderer, iOS has Metal, Android, we can use Vulkan, the cameras, and the way you interact with them. These are all different on the platforms, media encoders, decoders, audio players. These are all system libraries on the platform itself. We also have a thing on iOS where if you have a device that has a depth camera, so iPhone X and above, some of the newer tablets, we want to use ARKit for face tracking. Otherwise, we want to use our bespoke face tracker that we wrote for all the other devices that don't have this. Now, these resources are external to the engine, but they're definitely something that can be injected in at compile time. We don't need any iOS camera for an Android build, but there's also one other thing to consider here, and I kind of touched on it a bit in the spiel of what the app does. The kid does a recording bit, it does a playback bit, it does an export bit. There's basically 3 phases that the engine works in. Now, the other thing is that the engine doesn't need all those resources depending on the phase it's in. For instance, in interactive mode, we have a camera, we have a face tracker. And during that phase, as I mentioned, that all gets serialized to disk. So in playback, we're just reading from disk. Don't need the camera, we don't need the face tracker. On export, we don't need a surface to render to. It's just a pretty screen with a progress bar. You don't need to see the contents. We don't need a real-time clock. Like, we really don't want a real-time clock. we want to just bang through this thing as quickly as we can. So there are substantial differences to the resources that are required depending on the mode. The actual main loops themselves are quite different. From the interactive mode, the first thing that the interactive engine does is it locks the camera's frame distributor. Every graph has to get the same frame, or it's just, bleh. The interactive mode processes a whole bunch of commands. So other things like start, stop, they're the basic commands, but we can insert EDL events. We can look at what's running. We can remove things from running. It's a full interactive experience where, everything's changing. And again, export has to manage its clock. It's not a real-time clock. We need something to actually say increase the frame. So back to this question, is this all? With all this apparent kind of stuff that can change and happen all based on runtime, is this really a static decision? Now, I'm going to break this talk up into two parts. We'll first look at how we did the DAGs, and then we'll look at how we handled the myriad combinations of linking all these crazy resources in order to build the DAGs. So, slight tangent here. I'm going to go back to this guy and just basically say, this is kind of that old mindset. This is the mindset of yesteryear. This is that one-to-one mapping. We have two effective video clips, right? That are basically the same structure, but a little bit different. What we want is more of a number of DAGs independently running. So we have to build the functionality that we actually want. We want the one that's doing the display part and a separate DAG that's actually doing the serialization. This becomes much more parallel. You can run these guys side by side. So now these two little code snippets that I've put there map pretty directly to the rough sketch that we've got here of a simple DAG implementation. We can see that we have manually sorted our simple evaluation order and call the node's compute methods and pass the output from the provider to its next node. This has a few things missing. Some obvious things is like, how does the frame provider accept both a frame stream and a camera stream and a video clip, you know what I mean? So things like that. This also raises a few questions on how do we construct these guys? So each component is going to need some of these external resources we talked about before that take some unknown time to load from disk. I'll touch on this later. But after we have a peek at what, say, maybe the frame provider looks like, the frame provider component. So up here, we've got basically, you can see this dynamic dispatch and the static dispatch. There's not a hell of a lot of difference between the two, but the static version does require more typing, literally, figuratively, in all meanings of the word typing in this context. So we'll bring our static type back. So now we have a video clip graph that is generic across the timepiece, so real-time clock, monotonic clock, and a frame stream and the renderer, depending on platforms. The video writer we can see is generic only over the timepiece because we know that it's basically encoding a video that's coming from the camera stream. So we can just bake that guy in there. Now, this is a technique we try and employ. Only bubble the generic types up as far as we can. And this gives us some measure of control over the monomorphization and executable size that tends to happen with this kind of design. Now, somewhere deep in the bowels of the engine, we create this frame type on a per frame basis. So as you can see, it holds a dynamic reference to each graph that is to be evaluated for this frame. And the trade-off here is that we might be only holding 4 or 5 graphs, but a graph might be built out of hundreds of components. So instead of having dynamic dispatch on all the components, we're dealing with 5. And above this, we can see the trait that each graph is kind of generalized on. Now, the first method is a start method. Some components require an explicit start. So the graph itself has been built on some thread somewhere. It's come back, it's stuck in a list, and it's waiting to be scheduled. It has a frame number that it's due to be scheduled on. As soon as it's scheduled, it calls its start method. And the reason for this, well, at least one of the use cases is that we use clocks quite generally. So we have a master clock, which is basically running at the the master the master timeline's sort of playback speed, but we use clocks that might tick slower to meter out content at different rates. And so once the component is scheduled, it hits start, it's hitting its stopwatch. It knows that it might have to wait 3 frames, from a relative perspective to do its next thing, but it needs to know the first frame it starts on so it can start its clock to sync with. Now, because the components need a start, the graph needs to call a start. All components that need a start can be put in that start method. And finally, the meat and potatoes, the evaluate method. Each graph is then evaluated on a thread pool. We have a whole bunch of graphs that need evaluating, just throw them onto a thread pool, they get evaluated. At the end, they come out, there's data. So they're all evaluated in parallel. So now, inside the video clips graph of evaluation method, we have manually sorted our DAG and we execute it, and it's passing our inputs down, it's working. Right, now there's one other little thing where we need to do for this to get this to work. We basically want to have a builder type. We want to separate our construction behavior from an actual behavior. A few reasons for this. One of them is that a whole bunch of events have very optional parameters, and a lot of the parameters can be optional, and they have same defaults. We don't want to have to then, try and work out which parameters are not, the builder can decide the default. The other thing too is that the builders can be cheap to build. You can make one very quickly. The builder can get thrown on a thread, do all the resource loading that might take 400, 500 milliseconds while it's running its thing. So there are 2 main reasons why we use the builder. So again, here's the trait. We have a build type with a simple trait with an associated type that returns the type of the graph. We have our builder type itself. It's separate the init methods for all the inputs for the graph. And finally, the trait implementation that builds the graph type, right? So this is basically our full implementation of our video clip DAG. It's not bad, isn't it? It's pretty good. Terrible. Terrible. Bloody terrible. This is the simplest graph we've got by far, right? There is boilerplate up the wazoo. You remember these guys? Now, the track result, the mouth open logic, the catch logic, these little boxes are clearly placeholders for big things, many components, many components, right? Boilerplate becomes a whole lot of typing, and not the good Rust kind of typing. Like, I don't know about you guys, but I don't want to spend my time writing builders. Don't even want to write the evaluation method, right? Functions with that, all that manual node sorting. No, it's horrible, error prone. The only thing I'm interested in defining is the nodes and how they connect together, right? So can we take, the only bit I care about is that. Now, people who've written Rust here, does that look familiar? That kind of arrangement. How many times have you used a procedural macro to do that, right? Can we take this garbage and wrap it up into that, right? This is better. It's not quite enough to define a DAG, obviously. We need some extra annotations to define our inputs to create edges. We need a little annotation to say this component requires a start. And we also need a way to tell the graph how to build its components. So which parameters and which resources it's going to need. This is basically the complete implementation of the video clip DAG that we have in the engine, right? It's a reasonably nice, simple, declarative style for creating fairly complex functionality from a library of composable pieces. Now, by using a procedural macro for this, we gain not only the benefit of auto-generating all that tedious boilerplate, but the macro, in order to generate our evaluation function, has to sort all the nodes into its evaluation order. So if you inadvertently introduce a cycle or produce a DAG that's wrong, it's a compilation error. So we'll take a look at a slightly more complex example. This graph basically takes a frame from a frame stream, doesn't care if camera, video, tracks the face and renders the 3D mask over the user's face, plays a sound effect when the user does something such as open their mouth. That's it. So this is taken directly from the engine. I chose this one because it fits on a slide. This graph demonstrates a few interesting things and some of the more advanced functionality that we extended the system with. So firstly, I want to draw your attention to the, both the face provider node and the generic Kaiju face provider type, and the mask node and the animated mask type. The animated mask face is actually what we call a compound component. It's basically a component filled with a whole bunch of other components. This one in particular is built up of 12 other components, and that allows the mask to have animated textures, do blend shapes, scale of animation, do some physics, and then finally submit this mask for rendering. The face provider is also along these lines. As I said, our engine supports a bunch of renderers. It supports our bespoke, face tracker. It supports our bespoke face tracker 2-face. It supports ARKit. We've recently integrated ARCore. All these three different technologies have completely different compound components. They're completely different. So the ARKit and ARCore both basically wrangle data that's coming from an external tech. 2-face is literally built out of the component system. So the interesting thing about the 2-face component is that it isn't just about calling compute functions. We have a whole bunch of Rust code sort of intermingled with the various component computes, where we sort of inline implemented like a frame-to-frame tracker, where we don't have to do a whole bunch of stuff. Short circle, it worked out pretty well. The other interesting thing at the bottom is the graph that uses a few signal primitives written by my man Nick here. Yeah, it's really good. Now, these signals, basically the threshold signal is a component which opens a gate and inputs mesh, opens a gate when the input meets a threshold. The cooldown signal basically opens a gate when the input is true and a specific amount of time has passed. Now, these nodes, you might sort of say, they're basically like 2 or 3 lines of Rust. Why would you bother making a component out of these guys? A, because we're using static dispatch, the compiler can just say, I'm not going to call a function for that. That just gets inlined. We don't care about it. There's no performance overhead. 2, in the future, when this thing becomes a plugin, these nodes get exposed to users who are using a UI to drag and connect stuff. And then that can basically, it enables artists to, and not programmers, to build these kinds of graphs. So these DAGs are pretty cool, but they're also pretty useless if you can't give them any data. So we've seen that a video clip event has multiple meanings based on what mode the engine is running in. So it's either taking a camera session and displaying it while serializing it out. That serialization part's optional. It doesn't have to do that. And in playback mode, it's just reading an MP4 and playing it and drawing it on screen. Many other events have this kind of multiple interpretation. Some events have absolutely no meaning at all in certain contexts. The other thing that I think gets overlooked a bit with this kind of stuff, when people are being really clever with their generics and all this kind of stuff, you always have to specify the concrete types somewhere. You have to. It doesn't work if you don't. So over the next few slides, I'm going to skim over the sort of way we configure the engine. So in this slide, the interactive factory, we're genericizing over the graph factory, basically because the face trackers are external. So we don't know exactly what the resource type's going to look like. But with our playback factory, we don't need to bother about the graph factory. It's a constant type. We know we have a bunch of resources. They're fixed. They're inside the engine. We can just limit it to this guy. These are the highest level types that we have in our engine. They basically just contain that main loop. All 3 of those guys contain this one, this type. This is the real body of the engine. And this is the crux of how we sort out which combinations of graphs get built with each event, depending on what's going on. So again, some bowel surgery. As you can see, as the engine is running, we're basically looking ahead So we've got our frame counter here. We've got something ahead, looking ahead, saying, oh, these events are coming up. We want to convert those guys to graphs and have them stuck in our pending queue. And this happens basically via this snippet. So as you can see, the Graph Factory is basically being given the event and told to build all the graphs required for that event. So let's take a look at how this trait actually works. So this is our Graph Factory trait definition. Now you can see we actually have some implementation within the trait itself. This behavior, so the implementation here is basically how we're basically doing all our async building of graphs. And then we send it off to a thread, and we basically set up a little receiver that says, when you're done, send it to me. And that's basically what happens inside this trait. Now, the build graphs method is basically calling a generic version of the generate graphs method. And this is the bit that actually does that mapping. So going back to the idea that generics must have their concrete types defined somewhere, these become the concrete types for our Graph Factory based on what platform we're running on, which is why they're still genericized. They're obviously coming in externally. And we also throw the timepiece in there because, export is just such a special little cookie and has to do its own thing. So basically the Edl Factory is the start of where we give our sizes some types, give our types some sizes. It's a fairly small type that implements Graph Factory. And basically the generate graphs method here is building a little lightweight package of data to construct, basically to do with where the event needs to synchronize to, where it starts. We basically then look at that and we then dispatch on the event itself. Now, I'm not going to go into the definition of what the enum type is itself. It's basically just a big enum. It's all just basically using enum dispatch. But most of this code is actually also code generated from a descriptor file that we made. The main reason for this code generation descriptor file stuff is to A, remove boilerplate, but to enable tools such as like an EDL editor, which is a web tool that we have, to basically read this descriptor file and basically create EDLs correctly. And we follow this pattern in a bunch of other places in the engine, such as generating render pipelines, shaders, that can then be read by our tools for Maya and all these kinds of things. So they're all basically reading this one descriptor file and working from the same source. Now, so let's take a look at, So back to this slide, the EDL event processor trait is what we're going to look at next. So this is what the EDL event processor trait looks like. There's a pattern here in that we are putting a lot of our implementation in the traits itself. This is the default implementation of event processing. It's not the whole thing, I've kind of truncated it off. But this is basically used by the playback and the export engines. And because it's a trait, we can actually inherit the interactive processor from it. And then for very specific events, we can override specific behaviors. So for generating a mouth catch game, for instance, in playback mode, doesn't mean anything. In interactive mode, it means something. We can implement it there. So I'll just go back, sorry. This is also the bit where we do that linking of event to basically a builder function. This is the thing that generates our graphs. So if we take a peek into one of these builder functions, we're picking on video clip, we'll stay there. You can see the return type. So, sorry, let me just back up a bit. Remember this guy? This is where we store all our dynamically dispatched graph evaluator guys. And these are basically executed every frame. It's this function that generates that type. And so all the build functions will return the abstract graph type. So now to get there, we want these build functions to work with a whole bunch of resources. They don't need to know or care what they are, just so long as the resources being passed down to them have all the things that they require. So back to our Graph Factory types. What is this external resources guy? Might not be what you think. So this is a trait we use to collapse all our external platform stuff into a single type. It's just a trait with some associated types. It's a compile time only thing. It doesn't exist at runtime. So how do we use this? Basically everywhere. These traits, so sorry, brain dead. So these are traits that we use to type our resources to the builder function. They all inherit this subsystem types trait and then define themselves a bunch of associated types that are basically then define themselves from those associated types in the subsystem traits. So things like we saw before on the other slide, engine resources, media resources, camera resources, all these things are traits that are built from that subsystem type. Now, back to the idea of concrete types needing to be defined somewhere. This is basically what external resources is. It's a compile time only type that houses all the types we need for resources. And it obviously implements subsystem types. So back to our factory types to close out the final piece of the resource puzzle. Where do these resources actually live? So we'll jump into this playback event processor guy. So basically the resources are housed conveniently in the type that actually needs to distribute them to the build functions themselves. We see how our playback resources structure that's inside the type, inside the event processor, is basically genericized on that subsystem types. And so this playback resources type basically houses all the specific types that are available for playback mode. So things, obviously you can see, asset vault, playback configuration, the executor, renderer, scene wrangler, there's a whole bunch of stuff. It's truncated. This again, basically is genericized on that subsystem types. This guy is also the thing that implements those sub-bundle kind of resource traits like engine resources and media resources. So now we can give a quick glance at the interactive event processor just to round it out a bit. So we can see here, the actual resource type includes a bunch of extra resource constraints. So we've got the camera resource, the face tracking stuff, and this is injected in because it's, as I said, the face tracking stuff's all external to the engine. It needs to come in. Now, one of the main benefits here is that we make certain decisions about platform, which face tracker and which mode the engine is in, above all these points of the code. So we can actually type these things quite appropriately. The thing I want to avoid here is passing along some kind of Uber resource bundle that may or may not have a camera. Are we using ARKit? We're using two-face. I really don't like having to check and recheck the decisions that have already been made. I don't want builder functions having to deal with a bunch of unnecessary optionals. Using kind of the way we've set this up, the builder functions themselves have a guarantee via the type system that the resource bundle that is being passed into it will have all the resources that it will actually need. Thank you. Yeah, so to answer your question, the procedural macro is important. Like most things code gen, it has pluses, it has minuses. If your IDE is not super good at expanding these macros, things become kind of opaque. It does neaten things up a bit. Yeah, we used it a lot. It was a bit of an experiment. Yeah, pluses and minuses. Actually, this is our first major Rust project. That was me just looking at macros going, let's just see what we can do with it. Without code generation. It's actually pretty small without code generation. It's not super huge. With code generation, it's pretty big. I don't know, to be honest. Kind of fine, actually. You're basically just parsing Rust code in symbols and stuff like that. It wasn't too bad. Trying to. I don't remember having many super troubles. I think it was just the documentation. A lot of the code in the crates themselves, you can just go through and read it. Yeah, I guess I was just digging around and worked it out pretty quickly. Like the macros themselves aren't super complicated. All I really was interested in was the name of the structure, any kind of generic parameters, where sort of trait restriction type thingies, and then you're basically just splurging out a bunch of Rust code, sticking those little bits in. So it's not like a super complex procedural macro anyway. The descriptor ones are a bit different. They're not those derived macros. Sorry. So it's interesting. There's a bit of a timeline. So to answer your question, the decision around face tracking, how did it work? There's a bit of a timeline. So as I said, we wrote the original kind of prototype for this in Swift, sorry. We weren't sure exactly how far this project would go. So the client was a bit of a startup. They wanted to just make an app, see how it goes. We weren't sure if it was going to be the embedded chapter or the mobile chapter that would take the project on. There's a bunch of interesting things that went on. I started originally trying to write the Swift prototype in using some more static dispatch. The mobile guys were like, oh, this is not particularly Swift-like. Let's undo that. It did impact runtime performance quite a bit. Enough that I wanted that time back at the end of the project. And we developed our own face tracker for this project. And it was kind of towards maybe 3/4 of the way through that ARKit, that Apple dropped ARKit with their face tracker. That's when the iPhone X dropped. And there was a whole bunch of politics and finangled stuff, but we ended up basically sort of via Apple's encouragement, were encouraged to incorporate ARKit. So that was when we sort of had that was when that dichotomy was kind of introduced. Yeah, so this all happened before. So those kinds of base technologies were kind of developed a bit before we moved on to Kaiju itself. So we didn't know, we used the prototype, threw it away, as you do with all good prototypes, and took all the lessons from that to design Kaiju itself. Oh yeah, yeah. It's on. There's 3 apps. I think the original Wiggles app is still using the Swift engine, but Wiggles Android, iOS, so Oddbod, Sesame, iOS, Android, and they've got another thing in the works. They're all on the App Store. Yeah. The debugging bit's interesting. Going to Andrew's point, with the DAG stuff, like we hadn't quite got all the tooling quite there, and when you hit a problem with some of the DAG stuff, it could be a little opaque, especially if you're actually working on the procedural macro itself. So you definitely want to set up mechanisms for that early on. The typing stuff, I don't know, what was your experience?
eventually, you almost run out of single letters on some types. To render a T, but type T, you're going like, oh, T for the face. Yeah, so there was a lot of, you had to add one member down here, you parameterize this type, then you populate enough bound
Yeah. We did make a.
So it could have been better about doing like kind of grouping some of the more commonly occurring together traits like a super trait.
Yeah, which is kind of what I think during Sesame and Oddbod's development, we did make a bunch of mistakes. Like we ended up with graphs with all the face tracker inlined for ARKit and then another one for Two-Face. And we had all the game loops kind of duplicated. Anything that used face tracking kind of ended up with duplicated graphs. But that's when we kind of, I think that might have been after you left actually. We kind of collapsed all that into these, we kind of collapsed all these guys in. So we are passing those kind of traits of super traits where each individual face tracker is like its own thing that gets injected into a game loop. So that graph exists once, the builder exists once, everything exists once, and you just inject all the things you want. So we did sort of, after this mad splurge of writing code, we did work out where how far up those generic types need to be bubbled up, and we basically just clamped them there, rather than trying to push them all the way to the top of the engine. So we did learn a lot doing it. Yeah. Sorry. Yeah. Yep. Yep. Yeah, a lot of that stuff. So with regards to sort of the GPU/CPU usage for the graphs, obviously the rendering, basically we have like, if you can think of the engine as a data transformation pipeline. We have the initial ingestion of the event. It all splits off into parallel processing, and then it all converges at the end for rendering. So we do all our heavy CPU stuff there, and then we basically have a layered system with a compositor that goes and renders our frame. So a lot of the asset loading is loading texture sequences or heavier meshes, and then they all need to be taken from the bespoke kind of format that we use that we export out of Maya, put into a GPU-ready format, all these kinds of things. That all happens as part of the build phase. And then that gets sort of transmitted through the graphs, and the sort of blend shape parameters, skeletal sort of frame stuff all happens during the DAG evaluation. And that's basically set up like a little data thing that gets sent to the GPU and that gets rendered. Yeah. No. Particle stuff we don't do our particles on the GPU. That's all part of the DAG. I think, yeah. Yeah. Yeah.
Think of it in terms of like this is kind of more of your simulation update stuff, still at fairly traditional high levels rendering and process.
Yeah. In this engine, we use Vulkan. That CFG platform stuff is done under that hood somewhere. So yeah, we didn't have to cross that line. We have done other projects. A colleague of mine was going to do a talk about the various rendering stuff tonight, but he wasn't able to make it tonight. So further future meetups, probably able to answer all your questions, actually. Yeah. Yeah. Kinda. It's, as I said, it's kind of it's a thing that exists. It's compile time only, so it doesn't actually have any kind of runtime effect, but it kind of basically allows you a way of using a, say, generic trait with associated types and turning it into a concrete thing that's literally only carrying types. And then you can build an abstraction that is compile time only, has no runtime. It's a zero cost abstraction, ultimately. It's magic. Yeah. Yeah, it's okay. Like, so Swift has a fine C interface. We just do everything through C, like a C interface, through Rust. Obviously, you're going from Swift. So the actual layering is we have the Rust engine. Under that, we have some Swift stuff. And then on the top of that, we have some Swift stuff. So we present a Swift API to the apps, but we're also managing all our camera stuff, and the platform specific stuff is in Swift. And then we basically just have a fairly smallish C API that we sort of use as a layer to transmit stuff across. So there is a bit of unsafe. Obviously, it's a C API. It has to be unsafe. The Rust compiler can't verify that. But it is trapped at that level. So it's just, you know, a little wrapper around a C call. And that's how we do it on Kotlin as well. Yeah. Yeah. So there's a few things like the procedural macros have gained a bunch of stuff that weren't there. We had to encapsulate everything in strings. Don't need to do that anymore, I don't believe. It's all kind of still very rusty inside those strings, which I didn't really like. That was just because I was lazy and didn't want to get into all the nitty gritty of doing all that stuff, and I can just stick it in there. In terms of this engine was originally written asynchronously with, I think, Tokyo. And then we basically just pushed it all into async await later. So it was all just Rust native futures. Yeah. Trying to think of anything else. We've started using some const generics in there somewhere. So I can't remember what version that is, 1.6 or something. Rust, the thing is, like Rust, one of the good things about Rust is it does the versioning. So the 2018, we're just using whatever's in 2018. So this is limited to 2018 edition. Yeah, hope it doesn't break in 10 years, which we have no guarantees of, but, you know, what else. That's interesting. Yes, no, maybe. Shader C is still the biggest thing. So if you do a full checkout and build the engine, Shader C is by far the biggest build. Yes, there is compile time overhead. I will not shy away from that. That is a thing. So we do have a whole bunch of, we've basically gone, in this particular engine as a bit of an experiment, we just went full on crate instead of mono crate. It's just lots of little crates, which actually kind of suits me quite well from a test-driven development perspective, where you can just build this one crate. You write a test, you run it, it takes under 10 seconds. Yeah, it's the feedback is quick. So my approach to TDD has very substantially changed since using Rust. I don't care about whether something is being tested for its proof of correctness. The compiler does that for me. I use it more as a way of sort of exploring ideas and setting up and looking at the way client code is going to call the thing I'm writing. So it's more of a design tool or an exploration tool. The fact that I can assert something is true is an added bonus. So yeah, it's changed quite a bit because Rust is good.